Hello and welcome to the Northwest Quantum Nexus series. But before I turn it over to our host, Ben Lohr from Pacific Northwest National Laboratories, who will introduce our esteemed speaker, Will Oliver, I have a couple of housekeeping items to cover. First is a disclaimer that this seminar is being recorded. By attending this meeting, you may appear as an attendee in the recording. Your questions and comments in the Q&A will also be part of the recording. Second is a code of conduct. NQN is dedicated to providing a respectful, friendly, professional experience for everyone, regardless of gender, sexual orientation, physical appearance, age, race, or religion. We do not tolerate any behavior that is harassing or degrading to any individual in any form. Individuals are responsible for and knowing and abiding by these standards. We encourage everyone to assist in creating a welcoming and safe environment. NQN reserves the right to refuse admittance to or remove any person from an event at any time at its discretion. Now I'd like to turn it over to Ben, who will introduce Professor William Oliver.
Thanks, Mark. So I am Ben Lohr. I am a physicist at Pacific Northwest National Lab. It's my pleasure to introduce Professor Will Oliver, who we have collaborated with for a couple of years now on some very interesting experiments. I think he might touch on those in this talk. So Professor Oliver, my notes have gone here. So he's a jointly appointed associate professor of electrical engineering and computer science at MIT and a fellow at Lincoln Laboratory. He's the director of the Center of Quantum Engineering and associate director for the Research Laboratory of Electronics at MIT. Will's research interests include material growth, fabrication, and measurement of superconducting qubits, as well as the development of cryogenic packaging and control electronics. Will's a fellow of the American Physical Society and a senior member of IEEE, and he served on several national committees on quantum science and superconducting electronics, which I won't go through the whole list. And he received his PhD from Stanford in 2003. With that, I will hand it over to Will. Thank you.
Great, thanks, Ben. Let me start sharing my presentation. And while I'm getting that set up, let me thank the organizers for the invitation to speak today. And it's also really a pleasure to see so many friends in attendance today. So I really appreciate that. So let me get a pointer going. Good, I think I'm set up. No complaints, I'm going to keep going. So anyways, yeah, it's really a pleasure to be here. I'd like to talk about quantum engineering of superconducting qubits. That's a really generic title, so I will talk about something more specific than that. So let's get right into it. Yeah, so before we talk about quantum computing, I think it's worthwhile to go back and look at the last century of classical electronic computing. The vacuum tube was invented in 1906. This was the triode vacuum tube. It was used for radio transceivers, amplifiers for many decades, but it wasn't until 1946 that we saw the first vacuum tube-based computer called ENIAC from the University of Pennsylvania. Now, the next year, we know the transistor was invented. This was bipolar junction transistor. And within about 10 years of that, we had the first fully transistor-based computer called TIXO, or TX0, developed at MIT and at Lincoln Lab, but it didn't look anything like the computers we have today. You can see it takes up a whole room, but basically it was soldered transistors together and magnetic core memory was how it worked. To get closer to what we're familiar with today, we first needed the integrated circuit, developed in the late 50s. And then you fast forward maybe 20 years or so to get into the 70s, where we started to see the first, what we would call integrated circuits. So this is the Intel 4004 that I'm showing here with 2,000 transistors. Fast forward 25 years to get to the 90s and the Pentium Pro, where we now have millions of transistors. And then fast forward another 25 years or so to get to where we are today with multi-core processors, billions of transistors and graphical processing units. So looking from today back, it's been well over 100 years, right, of development since the first fundamental logic element to these, fantastic computers we have today. Now, quantum computing in comparison, of course, that's the setup, right? Quantum computing in comparison is much more nascent. As we know, Richard Feynman, Uli Mannin, and some others suggested in the late 70s, early 80s that if you want to simulate quantum systems, you should use a quantum system or computer to do that. And it took 15 years or so before we started to see the first quantum algorithms for, for important problems like cryptanalysis, Shor's algorithm, or Grover's algorithm for search, adiabatic quantum computing and quantum annealing. The first error correcting codes were proposed around this time. And by the early 2000s, we had seen a demonstration, in this case of Shor's algorithm, that 15 equals 3 times 5 on an NMR liquid state computer. And then fast forward 20 years or so to where we are today, which is that we have quantum computers that are available and accessible in the cloud. What I show here is superconducting, but of course now they're also trapped ion quantum computers you can access. And there have been demonstrations of quantum advantage, and we're getting closer to logical qubit demonstrations. So that's fantastic. And what is the takeaway? Well, first thing is quantum computing is real. It's transitioning from what you might call a laboratory or a scientific curiosity to technical reality. That's happening right now. But we also recognize that advancing from fundamental discoveries to useful machines is going to take a lot of time, and it's going to take a significant amount of engineering. And maybe one other takeaway is that you need to be in the game if you're going to play. And what I mean by that is that the companies that are building these fantastic chips today have been in the field for a long, long time, or they acquired companies that were in the field for a long, long time. So if we neck down for a moment to superconducting processors, I'm showing some pictures here of, here's Google's Sycamore chip. This is one of IBM's earlier chips. This one I think had 16 or 20 qubits. Righetti's 20 qubit chip. This is the backside of an Intel chip. This is just the connectors. I haven't seen the chip. This is D-Wave's machine, which is quantum annealing. That's of course a different type of quantum computing than the others, which are gate model. And of course, this guy in the middle here at the bottom is not a quantum computer. We recognize that as the Wright Flyer, where the first, flight in a self-propelled, manned aircraft took off and flew about 600 feet. And I think, this is basically the stage that we're at today. We're just getting off the ground, but it's really fantastic to see these developments. But of course, we want to do more. We don't want to just fly 600 feet. We want jet airplanes, and we want to, travel around and go on vacation. And for quantum computing, if we want to realize the equivalent of that, the full promise of quantum computing, we need to engineer quantum systems that are robust, reproducible, and extensible. And so I'd like to talk about, of course, that's a big topic, right? And, but I'd like to talk about a few areas therein that we are working on in my group at MIT and Lincoln Laboratory. So with that, let me get into an outline. I'll start with a brief introduction to superconducting qubits, get everybody on the same page. And then I'd like to talk about 2 experiments we've done recently. One is called density matrix exponentiation. That's an algorithm. And the other is a technique, which I think is pretty interesting, called quantum measurement emulation. I'll then conclude with some latest work on lattices of qubits that we're looking at, and also some 3D integration. So getting right into it, superconducting qubits are electrical circuits built from superconducting material, in this case aluminum. And you can think of it as basically an LC oscillator, an inductor and a capacitor. And of course, this forms a resonance circuit. It has a parabolic potential profile. And if we cool it down to a low temperature, where KT energy scale is much less than Planck's constant times the resonance frequency of this circuit, in that limit, this is a quantum mechanical object. It has discrete energy levels. You can label them 1, 0, 1, 2, 3, etc. But it's not a qubit in the sense that the transitions are all degenerate. And so it's not a very useful qubit anyways, because we can't uniquely address 0, 1 without exciting the whole ladder. So to get a qubit, we need one of these elements to be nonlinear, and the one that we choose is the inductor, because superconductivity gives us Josephson junctions, and these are basically nonlinear inductors. So Josephson junction is two superconducting leads separated by a thin insulating material. So aluminum, aluminum oxide, aluminum, for example, is pretty common. And Brian Josephson gave us the current and voltage relations for this device, but basically the point is that if you combine these together in the usual way to define an inductance, what you find is that the inductance is highly nonlinear in the current that flows through it. Okay, and with that nonlinear inductor, the Josephson junction, in parallel with the capacitor, we now get a potential shown in blue, which is a cosine, as it turns out. And now the consequence is that the level transitions are no longer degenerate. That means the 0-1 transition frequency differs from the 1-2, etc. And the degree to which it differs is something we call anharmonicity, and more anharmonicity is better. So this is just a very simple example known as the transmon, but it's one of a large family of artificial atoms that you can build from this concept. You can add more inductors, capacitors, and junctions to get different functionality, but it basically boils down to this. So that qubit is right here. It's called a fixed frequency transmon, but you can make the 0-1 transition tunable by opening up a loop that we call a squid with two junctions, and then if you apply a magnetic field through that loop, now the 0-1 transition is tunable. And you could add more junctions, as I said, or maybe even more. You might add a shunt capacitor, and generally you can just call all of these a generalized flux qubit. And you can engineer properties. There are design parameters that we can use. So as an engineer, I'd look at the critical current of the junctions, the capacitance of the junctions, or some capacitor that I add an additional capacitance, the number of junctions that I shunt it. I can think of that as a shunt inductance. The ratio of the sizes of the junctions. There's many parameters that you can use to set the properties that you want. For example, the 0-1 transition frequency, or it's tunable even, the degree of anharmonicity, or the sensitivity to different noises or sources of noise in the qubit's environment, flux, charge, etc. Now, we do choose that frequency to be around 5 gigahertz, and that's convenient because there's lots of electronics that is very, very good, developed basically in, I guess, concert with cell phone technology that we can use to control the qubits. But by choosing 5 gigahertz, that puts a constraint on the operation temperature. 5 gigahertz corresponds to 250 millikelvin if you just equate that energy to KT. And we want to be much colder than that so we don't thermally excite the transition. And so that means operate at, say, 20 millikelvin. 30 years ago, 40 years ago, the dilution refrigerator was, was the PhD project of many students. But today, these are just commercially available turnkey devices. And what you see here is about 0.5 meter in diameter, 0.5 meter deep. And this whole region is at 20 millikelvin. And you can see lots of familiar microwave elements inside, and even the qubit packages or resonator packages are shown here. So of course, these are circuits, and so we fabricate them, and it's a silicon technology. People may be surprised by that a little bit because it's superconducting, but the superconductors we use are all compatible with silicon fabrication, and in fact, we fabricate on silicon wafers using tools that are in a silicon foundry. So this is absolutely a silicon technology. What I'm showing here is a 200 millimeter wafer that's at a foundry we have at Lincoln Lab. If you zoom in on one of the many, many chips there, here's an example of 5 qubits in a row. Now we'll look at this in more detail later, but there are 5 plus signs. The plus is a capacitor. And if you look to the upper right, this meander is a resonator that we use to read out a qubit. And to the lower left are the control lines coming in to control it. Zooming in further, you can see that capacitor, and the control lines are now visible here. And the inductive part, you have to zoom in further to see the loop with 2 junctions. And so putting a magnetic field in this loop tunes the qubit frequency. And then if you zoom in on one of these junctions, now we're at the 100 to 200 nanometer scale. And these are the Josephson junctions. So I mentioned that we control this with microwave engineering, basically, microwave components. And what that basically is IQ mixing, where I means in phase, Q means quadrature. They differ by 90 degrees. And we feed this mixer with a local oscillator, so it puts out a tone that's almost resonant with the qubit. And then we have an arbitrary waveform generator that generates an envelope at a much lower frequency. We might call it the intermediate frequency or the AWG frequency. And the mixer multiplies those two together. And what comes out is the enveloped pulse at the frequency which is resonant with our transition when you add these two together. Now, there's one other difference, which is that if you use the I or Q port, you're going to either get in phase or quadrature phase shift on this pulse. And so we're going to have that correspond to the X or Y axis of the Bloch sphere. So that's shown here. On the left is the Bloch sphere, okay, the planet Earth. The North Pole is state 0. The South Pole is state 1. This blue vector that's rotating represents the qubit state. And the red vector that comes in and out is the envelope of this pulse we were just talking about. Now, don't correlate the color of the Bloch sphere to what's on the right. On the right here, blue means in phase, and you can see now pi pulses rotating. Now we go to the quadrature phase, which is the y-axis. And if we have half the area, we do a pi over 2 pulse. That brings the qubit to the equator. And then another one brings it back up to the North Pole. And so just using this standard IQ mixing, we can control where the qubit is on the Bloch sphere. That's how we implement quantum gates. Now, if we look at the past 20 years, there's been a remarkable improvement in superconducting qubits T1 and T2, energy relaxation and coherence. And that's been, a result of research worldwide into materials, fab, design. All of these have come together to give this 5 orders of magnitude improvement in the coherence times. And you can read more about this in some of our review papers. And in particular, this one by Philip Krantz is Quantum Engineer's Guide to Superconducting Qubits. So everything you want to know. At Lincoln Lab and at MIT, we don't have a favorite. So we work on many qubits that are superconducting qubits, like the 2D transmon, 3D transmon, C-shunt. We also have fluxonium. 0 pi qubits. But one question that we asked, and many have asked, is, how long is this trend going to go on for? And you can even see that it started to roll off a little bit. But is there a limiting factor to coherence in the future? What may limit us? And this led to a very nice collaboration with folks at PNNL. And Ben mentioned it in the introduction, but with Ben, John, Oral, and Brent Vandevender, we looked at the impact of ionizing radiation on qubit coherence. And ionizing radiation, whether cosmic rays or from nuclear decay, say in concrete of our lab, this radiation will split superconducting Cooper pairs into quasiparticles. And those quasiparticles are decoherence mechanisms. And what we showed is that, left unabated, just using the designs we have today, this would limit us to a T1 of 4 milliseconds. So that's about a factor 10 to 20 higher than the best superconducting qubits today in common use, but it's foreseeable that we're going to get there, right? And so we need to think about this. We showed that lead shielding helps in this experiment, and there are a number of ideas that we have to, in fact, mitigate quasiparticles, and these are in the form of, say, different materials or quasiparticle traps, phonon traps, etc. And this is research that we're also doing with these folks, as well as Ray Bunker, also at PNNL. Another experiment that we've done recently is this concept called giant atoms and waveguide QED. And I won't have time to talk about it, but it's really a cool science experiment. Let me just briefly talk about it. So if you have a natural atom or a superconducting qubit coupled to a waveguide at one point, the spatial extent of the atom is much smaller than the wavelength of the drive that we use to drive it. Okay, and so then the dipole approximation holds. But with superconducting qubits, because it's a circuit and we have wires, we can connect that qubit to 2 points along a waveguide, and those 2 points may be separated by a distance on the order of the wavelength. And so now this dipole approximation doesn't hold, and we need to consider self-interference due to the qubit emitting photons at these two locations and reabsorbing them with a phase shift. So that's really cool. And what it allows you to do is to couple to a waveguide without losing energy to it. You can have a destructive interference such that you never emit to the waveguide, and you can have two qubits coupled to each other via the waveguide without losing energy to the 50 ohm environment. And that's really useful because this is the foundation for quantum interconnects, getting information from one place to the other. We really don't want cavity mirrors or capacitors there when we're doing that. We'd like an open waveguide. And if you'd like to learn more about that, these two papers were published last year where we showed a Bell state fidelity of 94% in an open waveguide and the generation of a noon state, 2002 photon emission. But what I'd like to talk about today are some recent works on algorithms and how we've implemented them and high fidelity gates. And so we'll start with this density matrix exponentiation algorithm. And what I'm showing here is a punch card. Well, first of all, what I'm showing here is Barbara Liskop's hand. And Barbara Liskop, of course, is a pioneer in computer science. And what she's holding is this punch card. And what you can see is that representations of the data on the left and representations of the instructions that will eventually operate on that data on the right are both the same. They're holes punched in a card, representing numbers. And this is a concept known as Homo Iconicity, right? And that the representation of the data and the instructions is the same. The code and the data are the same. So if we look at and compare classical and quantum instructions, what we can see is, well, we just talked about classical instructions. You have some instruction set that's represented by binary data. That in turn is representing a Boolean logic circuit. Okay, that's the control layer. And that function is used and applied to data at the input and gives you an output. And you see that the data, as well as the representation of the instruction, it's all zeros and ones. Okay, classical data, Boolean logic. Now, in quantum computing, it's different. It's not homoiconic. The instructions are classical, right? We run these experiments from room temperature. We use a classical computer to decide what this circuit looks like. We generate all these pulses, as I just showed in the microwaves, at room temperature. We send them down in our fridge. They operate on the qubits, and it's only the qubits which are quantum mechanical, right? So it's only once you get down here that we start to see quantum mechanics in action. The instructions are classical. The quantum computing is quantum. So the question is there a homoiconic analog to quantum computing where both the code and the data are quantum? And that's a very interesting question, and I won't answer it in detail today, but what I can say is that we've demonstrated an algorithm where this begins to become possible. And it's called density matrix exponentiation. And as I'm going to describe, in this case, you have some qubits which are representing the instructions. And then you have some qubits, which are, of course, the data qubits. They hold the information. And the gates that you apply to the data qubits are determined by the instruction qubits. And that instruction state is unknown to us. It need not be known to us, right? So it's quantum instructions and quantum data. And we implement this using a density matrix exponentiation algorithm. Now, the one thing I'll show here, which is quite interesting, is that the evolution that we see here, as I'll describe, it's done through trotterization, through this density matrix over some rotation angle, plays the role of the Hamiltonian dynamical evolution in this sort of conventional thinking that we have. So this is what density matrix exponentiation does. Okay. We did that with a single qubit, one qubit for the instructions, one for the data. And the way that it works is the following, is that the part inside here in gray is classical. It's a fixed protocol. And what this protocol does is it says, whatever the state in rho is, use that state to define a rotation axis that we're going to operate on. I didn't show it here, but the data, which we'll call sigma, the data qubits, and you're going to rotate by an angle. Now that angle will be theta, but we trotterize it and divide it up into little steps, each step of which is delta. So this part is gray, but what I want to emphasize here, this is really important, is that what we apply in this gray box from room temperature is always the same. But the rotation that occurs is determined entirely by the quantum data. Okay. So density matrix exponentiation allows us to, load a program into a state, the instruction state Rho, and execute that program on another quantum system that we'll call sigma. And what we do is always the same, right? We're not doing different gates. The different gates part of it comes from the Rho. Okay. So it's been discussed at length that DME is efficient for implementing or generating quantum instructions, and it gives an exponential reduction in resource requirements certainly over any tomographic strategy. If you have an algorithm that you're running and the next step depends on the current state of your system, then you need to figure out that state. You need to do full state tomography, right? And that's exponential in the number of qubits, right? Okay. And the algorithm runtime scales only logarithmically with the dimension of the instruction state. And so I just list those references here. And so there are a number of papers that have been written over the past 5-10 years discussing different types of algorithms one could run using DME and relating that to this notion of quantum instructions. So here's the operating principle. Okay, so what we have is the target state sigma, this is the data, and then we have an instruction state, which we'll call Rho, and we'll then trotterize it into n steps. Now, what you could either do is have n copies of Rho, or you could take a single qubit Rho, or a single set of qubits Rho, and then after you use it, reset them and use the same ones over and over again. We have this swap operation, and if you remember what swap is basically this angle delta. You'll swap that delta. Now, remember that this does actually a 2 delta angle shift, but with sigma and Rho, sigma let's say advances by delta, and Rho will retard by delta. So there's a 2 delta between those two, but sigma only went forward by delta, right? And then we're going to throw away Rho, or reset it and come in with a fresh delta, or with a fresh Rho. And so just remember, like if this is pi over 2, then the swap that we get would look like this in a matrix form. So we implement this. The first rotation is on sigma is 1 delta, and we throw Rho away or reset it. We then do step 2. We get another angle delta. So now we've rotated sigma by 2 delta, then 3 delta, et cetera, et cetera. And we continue to do this for n steps, and this again is reminiscent of trotterization. And the error of doing this algorithm goes as delta theta. So the more steps you have, the lower this error becomes. Okay, that's basically how this works. In our case, we used a 3-qubit chip, but we only used 2 qubits on this chip, and one was sigma, one was Rho, and of course, again, to emphasize, in principle, we don't need to know Rho, right? In principle, we wouldn't know Rho if it was a quantum instruction, but to test this, we had to test it for different states, which of course we do know, right? And then we check if it works. So sigma is the target qubit, Rho is the instruction qubit, and we reuse the same one. So this is all n copies of it. So this is, just reiterating or presenting again that algorithm. And in this proof of principle demonstration, we implement one step at a rotation delta, and then we reset using a technique called quantum measurement emulation. And I'll talk about that next. But just think of it for now as a reset of Rho. Okay, Rho's reset now. We'll now implement another step of the trotterization, etc. Okay. And so this quantum measurement emulation approximately resets Rho after every rotation. I'll talk about that later. And of course, it introduces a small error in that. And the more steps we have, the less error it is. Okay. So let's take a look at an example of what this is. So the instruction state here is, in this case, it's the positive x axis. The number of steps we choose is 4. That's relatively small, but that's what we did. And the total angle of the rotation, this is a pi over 2 rotation. Now that is a trotterization of an ideal rotation around the x-axis of pi over 2. Okay. And sigma, I should say, we prepare sigma in plus y state. So I'll show a block sphere in just a moment. So the data qubit is prepared in y, the instruction qubit is prepared along plus x, and then we implement rotations delta, and then quantum measurement or emulation or reset, delta, reset, delta. We do that 4 times. And then what comes out is we'll measure that and do state tomography. We'll actually do it at each step of both sigma and rho. And this is what we see. So we start, let's just get our bearings here. What we're looking at on the top is the data qubit. The data qubit starts along y, and this is the block sphere, and then this is looking down or from the side, from the x-axis side. So the point is right here. And then it's plotted over here for x, y, and z. The instruction qubit is prepared along x, right? And you can see this projection here. So the instruction qubit determines the axis that we rotate the block vector or the qubit state around. And so after the first step, we see that this rotates indeed around the x-axis. We approximately reset the instruction qubit using QME. We take another step, we take another step, and we take our final step. And so we see that we've rotated pi over 2, 90 degrees. We see that there's some decay, okay, during this. And we can see that the instruction state was approximately reset, but there was some depolarization along the x-axis, okay. So this is an example of single qubit DME. The instruction state was along x, that's just shown here. And this goes into the exponent, as I showed before. And so this is the density matrix Rho given by this. And theta, again, is pi over 2. And basically, this looks like a pi over 2 rotation around the x-axis, right? And again, just to emphasize, this rotation axis was determined by Rho. We knew it here because we wanted to test it for a known case, but in principle, it need not be known. I'll also mention it need not be 1 qubit, right? This could be an n qubit aggregate complicated quantum state, and you would rotate the data qubits, which need not be 1 qubit, could be many qubits, around this quantum state defined by Rho. Right? Could be very complicated. Okay. So we can also look at another example where we rotate, in this case, again, we'll prepare sigma along y, but we're going to now rotate, we start, the instruction is in the 0 state or 0 state. We're going to take 8 steps, we're going to do a pi rotation, and this is what it looks like. So in this case, we're going around the equator, all right, you can see that here. Again, there's some decay, but we have gone 180 degrees, and the instruction state, which is along z, is depolarized a little bit, but is still along z after the reset. Okay. So, and you can see more about these experiments in this archive paper here. Okay. So there are a couple demonstrations that enabled us to do this experiment. And one is that we needed to have a high fidelity swap gate as well as a CZ gate, but in particular a swap gate. Our 2 qubit fidelities are now greater than 99.5%. The CZ, the best we've had, is almost 99.8%. And this iSwap fidelity is almost 99.9%. And this is work by Young-Kyu Sung in my group, and it was recently published in PRX. And the second thing that enabled this was this quantum measurement emulation. I'll talk about that next. For us in this DME experiment, it was a fast qubit reset or approximate reset. But as we learned about it and used it more, what we realized is it also allows error mitigation of stabilizers, and that's really powerful. So you can learn more about this in Amy Green's paper on the archive. So let me tell you about QME, quantum measurement emulation now. Okay. So of course, building a quantum computer is based on an architecture, and this one is due to Cody Jones, who was at Stanford when he did this. And it starts with the physical qubits at the bottom. You have your application and user interface at the top. There's a logical controller, just like with a classical computer. But what we see here are a couple layers that, while not unique to quantum computing, are very important to quantum computing. And one is open loop dynamical decoupling. and the other is error correction. Of course, quantum error correction is unique to quantum computing, but error correction is used in classical systems as well. And this quantum error correction layer, of course, you detect and correct errors, you do some gates, you may do some syndromes and decode, and you keep doing this over and over to basically obtain robustness through redundancy. You add more qubits and form them together into logical qubits. Okay, and lots of progress along these lines, and this is a holy grail to create a logical qubit. Now, because logical qubits are expensive, it behooves us to do anything possible at the virtual or the open loop layer to mitigate errors, and this is called dynamical decoupling. There's been a lot of work in that regard as well. And one example is the Carr Purcell or Carr Purcell Mayboom Gill pulse sequence, where you just apply pi pulses. Spin echo is a very simple example of this, which refocuses errors. And the reason it works is because if your noise has temporal symmetry and it's low enough frequency, you basically can invert the dynamics of your system with a pi pulse. And so, if you're going, forward too fast, you flip around and now you catch up, and basically you end up at the point you want to be at originally. So that's fine, but it requires noise with temporal symmetry. And in realistic algorithms, while you're running the algorithm, not a memory, but while you're running the algorithm, there is no temporal symmetry. You have all sorts of gates going on. And particularly in this NISQ era, it would be great if we had a way that we could perform dynamical decoupling whilst doing an algorithm, right? And so that's related to this quantum measurement emulation. So first off, let's think about the difference between incoherent and coherent errors. So if we just do randomized benchmarking, let's say in this case of the swap gate, and you have random, or the CZ gate, I'm sorry, the CZ gate, and you intersperse, other Clifford gates. This is Clifford randomized benchmarking. First, you do it with only the Cliffords, and you get that decay as a function of the number of gates. And then you do you interleave CZ gate with that, and you look for the difference. And the difference in the error rates must be attributed to this addition of this CZ gate, right? So you can get an estimate for the CZ gate this way. And you see that these decay basically exponential, has a nice exponential decay, and we would call that incoherent. But if you just apply a chain of CZ gates, right? If you apply two CZ gates back to back, that's basically the identity, so nothing should change. But what you see is that you get these oscillations, right? And these oscillations are due to coherent errors. And so these coherent errors build up over time. Each gate has a little bit of coherent error, and it coherently adds more and more and more. And these are really a problem. These are really a problem because they're hard to detect. And so one way around that is to do quantum measurement emulation, and I'll describe that. But the first thing I want to do is, before we do emulation, let's think about measurement first of all. So if we measure a qubit along the z-axis, here's the qubit state pointed off to the side, and our quantization and measurement axis is the z, the north to south pole. And we make a measurement. We're making a projection. This is an ideal projected measurement. And with a probability of magnitude a squared, we're going to project that to the north pole. And with probability magnitude b squared, we're going to project it to the south pole. And I didn't write it down, but the state here is A0 plus B1. All right, so just magnitude squared of those coefficients. Now, if we ensemble average that over and over again, vectors pointed to the north pole with this weighting and vectors pointed to the south pole with this weighting, we're going to end up with the vector shown here, which is depolarized. So ensemble averaging means identically prepare the qubit in the same state, make the ideal measurement, record the result, and repeat that over and over and over again. You either get plus ones or minus ones, and you average them, and you end up with something that looks like, I don't know, plus 0.8. All right. So that's standard measurement. Now we can think of and I should mention that this measurement takes a long time, right? It typically takes a microsecond. If you were doing feedback, you would basically get your measurement and then based on that, do some feedback to reset the qubit state. And that takes additional time. So this is very time consuming. But what we did instead is this probabilistic gate, which is pretty fast, 35 nanoseconds. We start with the qubit prepared in the same superposition state. And we do this quantum measurement emulation. And what that is probabilistically, we're going to do one of two things. With a probability 1/2, we're not going to do anything. We just apply think of it as the identity matrix. Okay. And with probability 1/2, we do a pi rotation or a z gate around the z-axis. Okay. If we ensemble average that, what you see is that the average of that is exactly the same as the ensemble average for this measurement, but it happened a lot faster, right? And in fact, we didn't make a measurement, at least in this upper case, right? We just said with probability 1/2, I'm either going to do the identity or I'm going to rotate around z by pi, right? And then I can do something else. So if you look at the tomographic reconstruction of the state, and now the top versus the bottom is measurement versus, again, measurement versus QME. We have this initial state, okay? And if in the QME case, half of the time we're going to do this rotation, and that would take us to the other side of the Bloch sphere. And averaging them together gives us this point in the middle, and of course, just doing a measurement gives us this point in the middle as well. But you can, of course, vary the angle of this initial state. And of course, we can do that down here. That's just preparation of the initial state. And we do these two protocols, and what you find is that they look basically the same. So that's why we call this quantum measurement emulation. We're emulating the measurement, the ideal projective measurement that we're showing at the top. Now, one thing to note is that, of course, that was around the z-axis. It can be done around any arbitrary axis. And what we're showing here is quantum measurement emulation for various states prepared around the equator. And we see that this projects onto, quote, ensemble averages onto the x-axis. Okay. So we can use the QME for state reset. That should say state stabilization or reset. Okay, and the idea is that you have your initial state, and then after some coherent error, you're going to do QME, which probabilistically will rotate it or not. You can repeat that over and over, and on average, you're going to get some slight depolarization. Now that's useful because this trace distance, and remember the trace distance is just the geometric distance between these 2 points, and then the trace distance here would be the geometric distance between these 2 points. Okay, that clearly is much smaller. The trace distance is much better with QME. And so we introduce an artificial error, just some rotation around the x-axis. When we start at the North Pole, we do some rotation. Then we do QME, and then we make a measurement. And we look at this, well, in this case, 1 minus the trace distance. So 1 would be ideal. And as a function of the rotation error, you can see that we get this quadratic improvement with QME. So the gray data, which is just basically no correction, you can see that decays rather rapidly. But the QME is first order insensitive for small errors. Okay, that's pretty interesting. So basically what QME does is it projects coherent errors that are transverse to the measurement axis, and it makes them look like incoherent errors. Okay, so we use that in the DME experiment, but then we realized, well, that's pretty interesting. I think we can use that for stabilizers as well. And so for these stabilizer codes, we perform basically a parity type measurement to distinguish states in a code space, right? And so for example, if your code space is 000 versus 111, this is a repetition code, you have these parity type measurements that you can make, and these are basically stabilizers. And the idea is that let's use QME to emulate these stabilizers and see what happens. And so, for example, one example is we could look at the code space here with a stabilizer ZZ, and now QME is probabilistically either doing nothing, so the identity on each qubit, or doing Z rotations, 1 on each qubit, that's the ZZ. Again, so if we first prepare that Bell state, we then do this is an artificial error, a rotation around the x-axis of theta, and then we do the QME. And what we see again is this quadratic protection, right, as a function of the error strength. So QME again, now by measuring stabilizers, gives us an improvement. Okay, that's interesting. And now we can actually look at the stabilizers with real errors, right? So let's create a circuit. In this case, it's a different Bell state. This one has a stabilizer of XX. And the uncorrected circuit would just be, let's apply some CZ gates, n pairs of them. So it's basically the identity over and over. And now let's interleave those with quantum measurement emulations. And remember, we only actually make a real measurement at the end, but we're interleaving now quantum measurement emulation between each pair of CZs, right, to see how it behaves. And what we see is that the first of all, the error is less with QME, and also it looks like it decays, you know, it looks kind of exponential-like. So again, these coherent errors that we know we have in the CZ are turned into incoherent errors. If we don't do quantum emulation, quantum measurement emulation, you can start to see the coherent errors oscillating, causing this to oscillate. So not only is the error more, but in fact, it oscillates again. So interleaving QME works. Now, one other experiment that we can do, and Amy's currently doing this, is you could compare dynamical decoupling, where you just do, say, a rotation on a pi rotation every time on those qubits, versus QME, which is this probabilistic identity versus XX stabilizer. And you can see again that the QME is performing much better than dynamical decoupling. And even though there's some structure here, maybe not very much. You say, look, it's just CZs, and then you have Z gates, Z, and etc. Despite that, we see that there's a big improvement by using quantum measurement emulation. And again, Amy's paper's on the archive if you'd like to learn more. I think I'm getting towards the end here, so let me just quickly say where we're at. I mentioned that our qubits have, our single qubit fidelities are more than 3 nines. The 2 qubit fidelities are about 3 nines. We're currently doing experiments on lattices, 3 by 3, and this is a 4 by 4 array. The 4 by 4 is in the fridge right now, but let me talk about a 3 by 3 array just briefly. In 2D, if you want to go from, say, in this case, point B to point A, as the crow flies, it's a certain distance, but in Manhattan, of course, you'd have to walk along blocks, which are left turns and right turns, etc. And so same thing in a 2D array. The distance from 1 to 9 would be counted in terms of how the crow flies, but of course, the quantum information can get from 1 to 9 by coupling in many different paths. And just showing this distance from 1 to 9, that's actually a Manhattan distance of 4, we can see through the experiment that the information starting with an excitation here just bounces back and forth. That turns out to be due to the high degree of symmetry, but it matches simulation very well. This is actually a Bose-Hubbard model, the way this is constructed with this always-on coupling in the hardcore limit, where the on-site interaction is much larger than the coupling between qubits. But it's a Bose-Hubbard model. And we've done a number of experiments. We've observed this quadratic speed up in 2D because the information has more paths to get from point A to point B. And we've done out-of-time ordered correlation measurements, localization, and we're currently working on multiple excitations. Let me just show you some results of localization. The nice thing about superconducting qubits is you can control each one independently, you can read them out independently, you can set their frequency independently, and you can do most of this simultaneously in parallel. So here's qubit frequencies are slightly different from one another that we can call disorder. Plotted against the disorder length, we can look at how the information propagates either in a 1D string or a 2D lattice. And in both cases, you can see that the data match simulation and theory quite well until you get down to what we would call the lattice size limit. We've also done Wannier-Stark type localization, where what this is you perform a gradient rather than random disorder. You have a gradient applied to your device. And if you start with an excitation in 2, due to this gradient, you see some breathing effect. The quantum information moves away from 2 and then it comes back to 2 and away and back. And these oscillations are called block oscillations, right? And in 1D, you can see the data match the theory again very, very well. We can also do it in 2D where we control both the gradient along X and Y. In this case, they're the same, but in the paper, you can see we did lots of different cases. But again, we get these block oscillations and the data match the simulation and the theory fairly well. And so last slide or two, we're currently building a system that's capable of measuring 64 qubits. This was due to a generous donation from Keysight Instruments, and want to thank them for that donation. But in there, we would do devices like this 4-qubit array 4x4, but you can already see long wire bonds, right? And that's because we just can't bring all the wires in laterally in 2D. And so that's led us to do and develop over the last 6 or so years 3D integration. And with 3D integration, what you see here, in fact, are 3 chips which are bump bonded together. There's the qubit chip, and that qubit chip is flipped over onto an interposer chip, and it retains its coherence because both of these chips or wafers are made with intrinsic silicon. So both of these are basically using a qubit-like substrate. And so it maintains a large mode volume. This gives us another surface where we can have additional active elements like qubits or tunable couplers. We also developed through silicon vias. These are superconducting and made from titanium nitride. They have very, very small form factor, so 10 by 20 microns, but 200 microns deep, right? So it's 10 or 20 to 1 aspect ratio. And then the third piece of this is the routing layer down at the bottom. This is an 8-layer niobium process. And so signals can be sent, think of California highway system, over, under each other, wherever they need to go until they get to the location in that lattice. And then the interposer will bring the signals up to the qubit and bring the readout signals back down. And I know that I'm totally out of time now, so I apologize that I won't be able to show, all these data. But here's just a picture of the superconducting through silicon vias. Some more pictures of that. Let me just show the highlight here that with this through silicon vias controlling and reading out the qubit, T1's around 41 microseconds. So that's basically what it is. This is the 8-layer wiring process from the side. We also use that to make parametric amplifiers. I realize I'm just flashing this. I apologize for that. But let me take time with the most important step, which is to recognize my colleagues at MIT campus and the Engineering Quantum Systems group, as well as at Lincoln Laboratory. This picture doesn't do justice to the total number of people. And also I'd like to thank and recognize all of the sponsors here who have made this possible. And thank you for your attention.
Thanks very much, Will. Very high information density talk there. Very interesting, though. So I am not seeing any questions in the Q&A yet. I know we've had some issues with it previously. So we had one from our panel, actually. This is from Kaimei. So regarding the quantum measurement emulation, you said there's a 50-50 probability for an identity or a rotation gate. Is that 1/2, optimal, or could you imagine different, a different random probability might be better in some way? Or is that a fundamental number?
Well, I think that if the goal is to basically symmetrize this and project onto this axis, then pi rotation is the ideal rotation angle. But if there was some other goal, then I guess that of course would be a different story. And in some ways this is reminiscent of randomized compiling, right? In randomized compiling, we also randomize the gates that implement the same algorithm. And by randomizing the gates and running the algorithm many times and then averaging over the results, we average out coherent errors, basically. And so you're left with incoherent errors for sure, but you average out the coherent ones. And this quantum measurement emulation is, in some sense, similar to that we're randomizing this quantum measurement emulation. And so, of course, we have to run it many times and then average, but that's what it is. And what's interesting is you can apply the quantum measurement emulation many times during the same algorithm, okay, get a result. And then, of course, you have to repeat the algorithm, use quantum measurement emulation many times, repeat, use it many times, and then average. Yeah.
And then a related question. So when using QME for qubit reset, do we need to worry about correlations among errors between subsequent resets? For example, if the coin flip fails to apply identity, then the error on the qubit remains the same as it was prior to the QME.
Yeah, so of course in the background there is decoherence that's happening, and that could be due to environmental effects, or it could be due to imperfections in implementing, as you said, the identity matrix, or in implementing the rotation, the pi rotation. And that's the reason that we saw this depolarization. You know, we're doing the reset, say along the z-axis, but as we implemented more and more quantum measurement emulation steps, we saw the polarization move from, you know, ideally at the North Pole, we saw it towards the center of the Bloch sphere. But it's interesting to note that we saw that it stayed pretty well on the z-axis itself, right? When we were doing the z version of it. So I think we do need to be concerned about those errors because it does cause depolarization, but we didn't see a lot of coherent errors manifesting themselves in that process.
Thank you. Let's see, another question. Are there already examples of quantum algorithms that make use of the Homo Iconicity?
Well, not too many, to my knowledge. I think there have been theoretical proposals, you know, or proposals for algorithms that could do it. And in one context in particular, in this density matrix exponentiation platform or context, I showed, I think, a number of papers related to that. But you know, there's certainly open questions related to this, right? Which is, you know, one is, how do you make that instruction state Rho in the first place, right? And of course, that can arise from many steps, say from the beginning of an algorithm when Rho is, say, prepared in its ground state, or maybe it's prepared in a massive superposition state. But you know, after several steps, especially for large numbers of qubits, that state is completely, you know, that's going to be unknown, and you know, tomographically determining it is going to be, you know, exponentially hard, exponential in the number of qubits. I shouldn't say it's unknown; it can be calculated, right? But at some point, right, that state becomes complicated enough that, you know, and in particular the rotation of the data qubits around that, you know, quote state. It's not just a single qubit now; it's an n qubit state. That's quite powerful. And how it's powerful because, you know, the way we do it now is we you know, deconstruct a complicated many body rotation like that into a universal set of single and 2 qubit gates, right? And we do rotations on single qubits and 2 qubits. We do a whole bunch of them to get the equivalent of a many body rotation in this language of DME. Now, how to program that computer, I think that's an open question, right, in general. And how to think about how to program that, I think, is an interesting question. So what we demonstrated was, you know, the 2 qubit version of this DME experiment. And I think it's very interesting to think about how this could be Homo Iconic.
So I'll insert a related question of my own. So if you have quantum instruction sets, to me that says that you need long-term quantum storage, which you probably other technologies are better at than superconducting qubits. You know, the vacancy qubits have much longer coherence times. Is anybody looking at, you know, making hybrid systems that kind of build on the strengths of the different qubit hardware types?
Yeah, there are, and so I think people have talked about connecting superconducting qubits to defect centers or to trapped ions, but there's a fundamental, I want to say it's a gotcha, but in most cases that I'm aware of, it's a gotcha, which is that if you look at these long-lived qubits like trapped ions or defect centers or nuclear spins in particular, they're long-lived because their matrix element with the environment is small, meaning that they're largely decoupled from their environment, right? So there may be lots of noise around, but I can't hear it, right? But what that means is that when I, as an experimentalist, intentionally try to come in and perform the rotation I want to do, that also is slow, right? And so that's the reason why, for example, trapped ions and superconducting qubits are basically neck and neck today. If you look at their, in real systems, their single qubit and their 2 qubit, in particular their 2 qubit error rates, are basically the same, right? Now the error sources are different and all that, but the point is that trapped ions run about 1,000 times slower than superconducting qubits, right? And so even though we're decaying faster, we're operating faster, and the ratio of those two, basically the decay time to the operation time, that's about the same. I can do 1,000 gates in a superconducting qubit, I can do 1,000 gates in a trapped ion, and then there you go. So, the point I want to make there is that if you're thinking about a hybrid system, these long-lived qubits generally are very slow. And you want to couple those to a superconducting qubit, and the coupling strength, the amount of time it takes to get the excitation or the quantum information from the long-lived memory to the superconducting qubit, the time scale that happens on is on the memory time scale. And that's going to, by that point, the superconducting qubits have all decoherent. And that's a gotcha for many of these hybrid systems, is that the long-lived memory is slow, superconducting qubits are fast. That's incompatible. So you want to find a memory that's really good, but has a fast operation time. And then the next potential gotcha is that, well, if I had that system, why don't I just use that system? It's fast and it has a long memory time. Why don't I just use that as my quantum computer? You would, and then you don't need the hybrid system. So that you have to work around that gotcha.
Very good answer. Okay, we're a little bit over. There was one last question that I think should be very quick. What's the footprint of the through silicon vias, and how does that compare to the size of a qubit?
Oh, I'm sorry. What's the footprint of what?
The through silicon vias.
Oh yeah. Thank you for asking that. So what I'm showing here is this is a fairly large qubit. Okay, this is the capacitor. This black dots that you see, those are RTSVs. If you look in the literature, some people have 100 micron TSVs, some people even have 500 micron TSVs. But if you want to make, say, a microwave transition, you need, say, 10 TSVs for this microwave line. And you can see in our case, we can do that pretty easily. If I had to make 10 of these 100 micron TSVs or 10 of these 500 micron TSVs, I mean, you just blown up the area entirely. So that's one statement. And then, the other statement, which I didn't have time to talk about, is that this 3D integration also allows you, and TSVs allow you, to further shrink the size of your qubits. In this case, the readout resonator basically fits underneath the qubit. And so then it just, reaches up through the TSV to sense what the state of the qubit is. So 3D integration is quite enabling in terms of reducing the footprint and improving performance.
Thank you. Okay. Well, thank you once again, Will. I think we're going to cut it off here. I believe the recording will be up, I think, for 30 days. I think at the same link and on the NQN website. So thanks again, and we're going to close it down here.
Great. Well, thank you very much, Ben, again, for the invitation, and thank you for your attention.